Okay, balancing redox equations. Redox equations that occur in aqueous solution can be difficult or virtually impossible to balance by inspection. That's the technique we learned, where you just look at it and you say, well, I've got this many of this and that many of that, and I need to do this and that. So there's a special procedure, and we call it the half reaction method of balancing. So what we do is we take the overall equation and we break it down into two half reactions and balance each of those separately and then put them back together. The two half reactions will be one for oxidation and one for reduction. So if we look at this equation, aluminum reacting with silver ion to form aluminum ion and silver metal. You might look at that by inspection and say, oh, well, that's balanced. But it actually is not balanced. Because in order for it to be balanced, the charges also have to be equal on both sides. On the left here, we have a total of a +1 charge, and on the right side, we have a total of +3 charge. That means that 2 electrons disappeared. That can't happen. So what we're going to do is, first, we're going to assign oxidation states so that we can clearly identify what's being oxidized, what's being reduced. The oxidation state assignment here is pretty easy. We have 2 elements, right? Aluminum. So that's a 0. And in the products, we have silver with a 0. We could do this without oxidation states, but we're going to practice. What's the oxidation state of Ag+? It's the same as the charge, +1. And what's the oxidation state of Al3+? That's +3. Okay, so which of these is increasing in oxidation number? The aluminum. The aluminum's going from 0 to +3. So that's the oxidation half reaction. Lost on my iPad here. So we'll take the aluminum solid going to aluminum ion, aqueous. That is a half reaction that just describes the oxidation. It can't happen by itself, and we're not saying that it does. We're just taking it apart so that we can figure out how it's balanced. The other is being reduced. So silver ion is going from +1 to 0. That's the reduction. So +1 to 0 is the reduction. In this one, we could use the charges to identify the oxidation and reduction, or you can use the oxidation states. Any questions? Next, we're going to balance each of the half reactions first with respect to mass. So making sure that we have the same number of atoms of each element. So if we look at aluminum going to aluminum, the element going to aluminum ions, we have 1 aluminum on each side. So that's already balanced with respect to mass. And silver ion going to silver, that's already balanced with respect to mass. Then we're adding something we're going to balance with respect to charge. Because this is not balanced with respect to charge. It's 0 on this side and +3 on that side. How does that happen? There's electrons involved. So what we want to do is we want to put electrons in either as the reactant or the product so that the charges on both sides of the arrow are equal. We're not subtracting electrons ever, we're only adding stuff. So to get these to be equal, I need to add 3 electrons to this side. So I go +3 electrons. The electrons have negative charges. So adding 3 electrons with this +3 charge gives me a total of 0 on that side, which is equal to the total of 0 on the other side. It's not always going to be 0 on each side, but it needs to be the same. And then down here, what side am I going to add the electrons on? The left side, because I have a charge there. So I want to add 1 electron because I have a +1 charge. So these charges now add up to 0, which is equal to the charge on the other side. And this fits in with our definitions of oxidation and reduction. Oxidation is loss of electrons. So here's the aluminum, it becomes aluminum ion and it loses those 3 electrons. Reduction is gain of electrons. So here's the silver ion gaining an electron to become silver metal. Now, the number of electrons that are lost by the aluminum has to be equal to the number of electrons that are gained by the silver. So each aluminum atom is losing 3 electrons, but each silver ion is only gaining 1. How can this be? Well, maybe there's more than 1 silver ion. Maybe there's 3 silver ions. Each of them is taking 1 of the 3 electrons that the aluminum is giving up. So what we do is we multiply so that we get the same number of electrons on both sides. Let me go back to this slide. So here I've got 3 electrons on this side, 1 electron on that side. I want to multiply one of these, or sometimes both of them, so that I can get those to be equal. I want 3 on both sides. So I'm going to take this bottom equation and I'm going to say, well, this must happen 3 times. So what that means is there's 3 silver ions and 3 electrons, and I'm going to get 3 silver atoms out of it. So that's what we've done here. Now what we're going to do, once we've got the number of electrons equal, we're going to add these together. So I've got 3 silver ions plus aluminum, and then I've got 3 electrons there, and an arrow, and then I've got the order that you put these in doesn't matter, as long as they're on the correct side of the arrow. Well, here I have adding 3 electrons and releasing 3 electrons. Those basically cancel out, right? Because the electrons are not actually seen. What happens is these 3 electrons that are given up by the aluminum go to these 3 silver ions. They're picked up immediately. And so we say those cancel out, and we just don't include them in the balanced equation down here. So that's our balanced chemical equation. You have to double check. Is it balanced with respect to mass? We've got 3 silvers and 3 silvers, 1 aluminum, 1 aluminum. Yes. Is it balanced with respect to charge? Total charge on the left side, plus 3. Total charge on the right side, plus 3. It's balanced. Any questions? So here's the list of instructions for how to balance these, the half reaction method. First thing is assign oxidation states. Next, separate the overall reaction into 2 half reactions. Balance each half reaction with respect to mass. Now the one we did was very simple. They can get a little more complicated. So what you do first is you balance everything besides hydrogen and oxygen. All of these are occurring in aqueous solution. So water has hydrogen and oxygen. Then you balance the oxygen by adding water, H2O, wherever you need it to balance the oxygen. And then you balance the hydrogen by adding H pluses. This would be assuming that you have an acidic solution. If you have a basic solution, you go one step further, and then you neutralize those H pluses by adding hydroxide ions. You just add the same number of hydroxide ions to each side of the equation. We'll do an example like that. Then you balance each half reaction with respect to charge using electrons. Then you make the number of electrons in both half reactions equal. You add them together and then double check that everything's balanced. So those are the steps. Let's do some examples. Balance the redox reaction occurring in acidic aqueous solution. So the first thing is, what? Oxidation states. What's the oxidation state of H+? +1. So hydrogen ion is +1. And what's the oxidation state of chromium? 0. Here we have H2. What's the oxidation state? 0. It's an element. How about Cr3+? +3. Monatomic ion. So the hydrogen, the H+ and the H2 obviously are going together, and the Cr and the Cr3+ are going together. Now, you can separate these into the half reactions without actually needing to think about which one is oxidation, which one is reduction. It could ask you that, but most of the time they just want you to balance it. So I'm just going to take the first one. So I see that I have H+, and this is going to H2 gas. So that's one half reaction. And then I've got Cr going to Cr3+. So I took the one reaction and I pulled it apart into two pieces. Any questions? So I need to make sure that it's first balanced with respect to mass. Is this first one balanced with respect to mass? Are there the same number of H's on both sides? No. Here there's H2. 2 H's, here there's only 1. So I'm going to put a coefficient of 2 in front of the H+ so that the H is balanced. The bottom one is already balanced. 1 chromium and 1 chromium. Next, I balance for charge. So here I have a total of +2 charge on the left and a total of 0 charge on the right. I need them to be equal, and I do it by adding electrons. So I'm going to add 2 electrons to the left side, because 2 H+ and 2 negative electrons, those charges add up to 0, which is equal to the charge on this side. It's like voodoo, isn't it? He's looking at me and smiling and shaking his head. I'm sorry. You signed up for the class. Here we have Cr, total of 0 charge here. Cr3+, total of +3 charge. So I want to add 3 electrons over here. So I've got +3 and -3, and that adds up to 0, which equals what's over here. Okay? On the top, the first half reaction, I've got 2 electrons. On the bottom, I have 3 electrons. If I add them together now, I'm going to end up with electrons in my equation, and I don't want that to happen. So I need to get them the same. So what's the least common multiple of 2 and 3? 6. So I'm shooting for 6 on each side. So what I'm going to do is I'm going to multiply this one on top. I'm going to multiply everything by 3. And the bottom one, I'm going to multiply by 2. And I chose those because 3 times 2 electrons will give me 6 electrons. And 2 times 3 electrons will give me 6 electrons. But I can't just do it to the electrons, I have to do it to everything. So I'm going to go to a different color here. So I'm going to multiply, when I multiply the 2 by 3, I get 6 hydrogens. And I multiply this by 3, I get 6 electrons. And then I multiply that by 3, and I get 3 H2s. It is still balanced with respect to charge and mass, because I did the same thing to everything. The bottom, I'm going to multiply by 2. So I'm going to get 2 Crs and 2 Cr3+. I'm going to multiply this by 2, and I'm going to get 6. Okay? Now I can add them together. So there's my arrow. I've got 6 electrons here and 6 here. So those cancel out. Let's maybe make this green. So 6 electrons and 6 electrons, they don't show up in the final equation. Kind of like spectator ions. They got just moved from one to the other. And I'm just going to copy down what's left. So I've got 6H plus aqueous plus 2 Cr solid. And then over here I've got 3H2 gas and 2 Cr3 plus aqueous. Double check, 6 H's, 3 times 2, 6 H's. 2 Crs, 2 Crs. Total of positive 6 charge over on the left side, positive 6 charge on the right side. Balanced chemical equation. Questions? Yes?
So before we got to this chapter, every other equation that we balanced, was that still correct? Or was it just like to learn that the basics before we could rebalance?
Okay, so what about all those other equations we balanced? We only gave you ones that could be balanced by inspection. Some oxidation reduction reactions can be balanced by inspection. Some cannot. So when we had you do the oxidation reduction reactions earlier, we were careful in which ones we gave you. And so now we're doing this. And you can only do this when there's oxidation reduction occurring. You can't do it for like a neutralization reaction where there's no redox. Let's do another one. Balance this reaction occurring in acidic aqueous solution. Okay, we have a limited amount of time, so I'm going to go through this a little faster. You can watch it on YouTube later and slow it down if you need to. So first thing, oxidation states. Well, copper is an element. It's got an oxidation state of 0. Here we have nitrate ion. So we think Fa765. Oxygen gets what it wants. It gets to be -2. There's 3 oxygens, each -2, so that's a total of -6 in oxidation states. And overall I need -1, so the nitrogen is +5. Here I have a copper ion, that's +2. Over here I have NO2. Similar situation to over here. The nitrogen has to just go along. Oxygen gets what it wants. Oxygen wants -2. There's 2 of them. So this is -4. Overall it has to be 0, so that the nitrogen has to be +4. So there's our oxidation states. I think it's helpful to just kind of group these before you split them up. The copper is going over there, and this one is going over here. So I'm going to write down CuS goes to Cu2 plus aqueous. And then I've got the NO3 minus aqueous going to NO2 gas. So I split it into 2 half reactions. Next I need to balance with respect to mass. The first one's already balanced. The second one, not so much. I have 1 nitrogen on each side, but this one has 2 oxygens, that one has 3 oxygens. Okay, just balancing by inspection, you can't do it. That's because water is actually participating here. So we balance the oxygens by adding H2O where needed. Well, I've got 3 oxygens here, 2 over here. I need another oxygen on the right side. So I'm going to get it by adding H2O. And that's not some hocus pocus. This is occurring in water. There's a gazillion and a half water molecules floating around. So I can throw one in there, that's fine. So now I've got my oxygens balanced, the nitrogens are still okay. Now I've messed it up, I've introduced hydrogen. This is happening in acidic solutions. In an acidic solution, the number of hydrogen ions outnumbers the hydroxide ions. So we're going to balance the hydrogen by adding H+. So I have 2 hydrogens on this side. That means I have to add 2 hydrogen ions on that side. Why hydrogen ions? Because we told you to do it that way. So now we have mass balance. Okay, now we have to put electrons in and balance the charges. So the first one's easier. We've got 0 on the left plus 2 on the right. So if we put 2 electrons over here, then we'll have 0 on both sides. Down here, I've got 2 H pluses and 1 NO3 minus. So I've got plus 2 and minus 1. That overall is a plus 1. And on the right side, I've got 0. So I need 1 electron over here. If you're doing this correctly, you're going to add electrons on the left of one equation and the right of the other equation. If you end up with them on the both on the same side, you're doing something wrong. So we've got mass and charge balance. We need to get the number of electrons the same. So this has 2 electrons, this only has 1. So I'm going to multiply everything in this second half reaction by 2. And I'm going to leave the top one alone. So here we're multiplying by 2. So that becomes 4, and that becomes 2, and 2, and 2, and 2. I did that because I want 2 electrons over here and 2 electrons over there, because when I add them together, they're going to cancel out. So now I add them together. So the electrons cancel out, and I just copy down what's left. And the order doesn't matter. Even mastering chemistry doesn't care. There we go. This is an example of a redox reaction that's really, really tough to balance without using this half reaction method. To do it by inspection, you're going to get stumped by this 3 oxygens on one side and 2 on the other, and you can't get them separated because they come with the nitrogens, and if you fix the oxygens, you mess up with the nitrogens, and you could go around and around all day doing that. That's no fun. Not even for me. So then you should double check that your mass and charge balance. Any questions? Yes?
In order to add an oxygen on the bottom right side,
Mm-hmm.
with H2O, is there a way you could have done that? Like you have to add
You have to add H2O.
but in order to add hydrogen,
You add hydrogen ion. So the method is that to balance the oxygen, you add H2O. That, of course, is going to cause a problem with hydrogens. You balance the hydrogens using H+, because that doesn't mess anything up. And there are H+ ions present in water. Any other questions? Yes?
If there was no water, if there was no oxygen balance, I mean, is there a situation where in acidic reaction like this, a solution where there's not an imbalance in oxygen?
Yeah, is there ever a reaction like this where there's not an imbalance in oxygens and you don't end up putting water in? Yes. In fact, the previous example was like that.
No, I mean, like, but you would still have to.
But like still having oxygen in here?
No, I meant like you said, would you ever need to add a hydrogen just to without?
You might have to add hydrogen without oxygens, without water, yeah. And so the order in the instructions is you balance the oxygens first. If they're already balanced, then you don't add water. And then you balance the hydrogens using H+.
So if you can't balance, that's when you have to add H2O, right?
Yeah, when you balance everything but the hydrogen and oxygen. So, you know, they were already taken care of. But I'm gonna take care of the copper and the nitrogen. I don't want to balance the oxygen and then try to add something in to fix the nitrogen. You're going to balance everything except oxygen and hydrogen because you can use water and H+ to take care of those. So let's do another example. Here's another one. So first thing is oxidation states. Tin is 0 because it's an element, and SN2 plus is +2, and MN2 plus is +2. And then MnO4, this is a polyatomic ion, and so oxygen is going to get what it wants, -2. There are 4 oxygens, each -2. Total oxidation state for oxygens is -8, and I have a total of -1, so that means that the manganese is +7. And yeah, manganese can do that. How did I do that? That's magic. Okay, so I got the manganese, I don't know, plus 4 times the oxygens, what each of them is, and I know that has to add up to -1. Okay? Now I'm going to take my half reactions. So this tin is going from 0 to +2, that's being oxidized. The manganese is being reduced. And I'm going to write them out here. So I've got, well, there's some space. SN going to SN2 plus aqueous. And then down here I've got MnO4 minus aqueous going to Mn2 plus aqueous. 2 half reactions. First, balance mass. Well, the first half reaction's fine. The second half reaction, the manganese is balanced, 1 on each side, but the oxygen's not. I'm going to add H2O to balance the oxygens. 4 oxygens on that side, so I'm going to add 4 H2Os on the right side to balance the oxygen. I'm adding 4 H2Os because that'll give me 4 oxygens, which will balance the 4 oxygens on that side. That introduces hydrogen, and we have to take care of that. I have a total of 4 times 2, 8 hydrogens down here. And so I need 8 hydrogen ions over here. 8 H pluses. That should be aqueous. Next, I balance with charge. So tin going to tin 2 plus. I'm going to have to add 2 electrons over here. And then this mess, I've got +2 on this side, and I've got +8 minus 1. What's 8 minus 1? 7. Got a total of +7 over there. So you might want to make some little notes for yourself. So I've got +2 over here, and I've got 8 minus 1, which equals +7 over there. How many electrons do I have to put on this side to get this charge down to 2? 5. I need 5 electrons. Because now I throw in the -5 plus 8 minus 1, and that equals +2. I'm not going to get 0 on both sides necessarily. They just need to be equal. Okay? That's in the way. Next, I need to make the numbers of electrons on both sides equal. Well, I've got 2 and 5. Least common multiple of 2 and 5 is 10. So I'm going to multiply these so that I can get 10 electrons on each side. So that means that the top equation gets multiplied by 5. So I'm at 5 tins, and I'm at 5 tin ions, and I'm going to get 10 electrons. The bottom equation, to get 5 into 10, I'm going to multiply by 2. So this becomes 10. 2 times 8. We're getting into some big numbers. Don't be scared. It's okay. And then this is a 2. And this is a 2. And 2 times 4 is 8. So I've got 10 electrons on both sides. I can add these two together now. Those guys cancel out. copy down what's left. 16 H plus 2 permanganate ions plus 5 tin atoms gives us 2 manganese ions plus 8 water molecules and 5 tin ions. And if you check that, it should be correct. Any questions? Yes? This will be on YouTube. I know, I'm going fast, but I'm still not getting through it all, which because here's the one in basic solution, and then the whole activity series thing. So what I'll do is I'll go up to my office and lecture to my wall and record this and put it on YouTube. Unless you want to stay. No, nobody wants to stay.